Okay, so the problem says here that a 3.5 kg block, this one, is accelerated by a compressed spring of spring constant 640 Newton. So this is the spring and its spring constant is 640 Newton per meter. The block leaves the spring at spring's relaxed length. So when the spring is relaxed, it leaves there and it travels over a horizontal floor with a kinetic friction of 0.25. So it travels over this floor in this direction, and the floor's kinetic friction is 0.25, if we call that mu. So that's there. The friction force stops the block in distance, that will be distance, this 7.8 meters. So it travels for 7.8 meter, and after that it stops because of the kinetic friction. So we need to find what are the increase in thermal energy of the block floor system. So the energy loss due to friction will be the thermal energy. So that will be equal to the weight of the block mg times the kinetic friction coefficient. So mu, that much. So mu is 0.25 and block's mass is 3.5 times 9.8. That's the force there, kinetic friction force, and that will be, when multiplied by the distance traveled, will give the energy. So that multiplied by the distance traveled, which will be, if we call that d, and d is 7.8 meter. We know it goes for 7.8 meter due to the frictional force, and after that it stops. So the frictional force stops it after 7.8 meter of movement. So that multiplied by 7.8 gives the thermal energy, or the energy due to frictional force. So that will be 67 joules approximately. So what happens is, because of the spring's potential energy, when the spring is released, that potential energy is transferred into kinetic energy of the block. As a result, the block was initially from rest, but when it is the spring is released, it gains its velocity from the spring's potential energy, and that, because of that velocity, it has a kinetic energy, and because of that kinetic energy it keeps moving in that direction. And that kinetic energy will be half mv square. V will be the velocity with which it starts moving, but that kinetic energy will again start dropping because of the frictional force. And when it stops after 7.8 meter, what happens is it doesn't have any more kinetic energy, because V becomes 0, and all that kinetic energy converts into the thermal energy, basically the frictional force energy. So that will be equal to 67 joule there. So also the question is, the second part is the maximum kinetic energy of the block. So the maximum kinetic energy will also be this much. Initially this was the total kinetic energy here, 67 joule, and then finally when it stops, all that kinetic energy is converted into the thermal energy of the block and floor system. So that's how the energy is converted from one to another. In this case, from spring's potential energy into kinetic energy of the block, and then finally thermal energy of the block and floor system. So that's there. So second part will be just like that, 67 joule. But if we were asked what is its maximum velocity, which velocity started, at this point it will have the velocity corresponding to, so half mv square would be 67. So v square would be, of course, 2 times 67 divided by 3.5, and v would be square root of that basically. So if we want to find v, I don't know, just remove that, and then that would be square root of that. That would be the maximum, the velocity with which it starts traveling down the floor, basically, the floor with friction. So that's there. Finally, the question is, the third part is original compression distance of the spring. So how much the spring compressed, that we need to find. So because of the spring's compression, the spring had a potential energy, and that energy is also 67 joule, because that's the potential energy of the spring, 67 joule, that is transferred into kinetic energy of the block. So spring's potential energy, then Bloch's kinetic energy, and finally thermal energy. But all are 67 joules. So here also, sorry, 67 joules. So here also the spring's potential energy is 67 joules, and we know we get spring's potential energy from this expression, half k x square, x being the displacement from its relaxed position. So if this is position 0, the spring's position, when the spring is relaxed, when it's compressed, how much it goes, that is x in this expression, that is x. So that is what we need to find. We need to find original compression distance of the spring. That means how much did it compress. So here that one will be equal to 67, and we can get x square will be 2 times 67 divided by, that's 640. So x will be 2 times 67 divided by 640 square root. So that gives 0.457 meters approximately, or we can say 45.7 centimeter approximately, or maybe 46 centimeter. So that much, that's the compression length of the spring.